Hey guys, welcome to another video in the Nice Question series. So today's question comes from the advanced course in the topic of financial maths. One of my favorites, I'm an actuary by trade, so financial maths, it's where it's at. Anything to do with like future payments, home loans, love those questions. So the question from today comes from the CSSA paper in the recent trials, so the 2023 trials. I thought it was a bit different. Let's have a look. Yeah. So with this question from the CSSA, I like it because it does something different, right? So let's see. Ada has 500 grand in an investment account earning 3% per annum. Nothing fancy there. Very straightforward. And then it goes, at the end of the first year, Ada withdraws to 25,000 for expenses, right? Now, I like this because a lot of the questions are quite typical. Like, for example, you borrow 500 grand on a home loan. The moment you hear like loans and stuff, your mind triggers a set way of doing things. This one here, normally when you invest 500 grand into an investment account, that's a superannuation question, right? And then it triggers a different type of outworking. Now, if you've forgotten how to do superannuation home loans, look at my earlier videos. I did a few videos showing you the structure and the framework that I would apply to questions like this. But this one's cool. So we save 500 grand, earning 3%, and then she withdraws $25,000 at the end of the first year for expenses. Each subsequent year, the amount that Ada withdraws increases by 5% due to rising expenses. So each year, she's withdrawing $25,000 with 5% extra each year. I like this, right? She's not withdrawing a fixed amount. That makes this question a little bit harder, right? So let A and B the balance, okay, and prove that. Now, let's start this question and develop the geometric series, right? I really like this. So, part A. So obviously A0, she has $500,000, right, earning in the investment account, right? At the end of year, is it year or period? Year one. At the end of year one, now what happens? The 500,000 earns 3% of interest, right? And then she subtracts $25,000 for the first time, right? That's cool. That's easy. That's sweet. A2. Now I know that A2 always develops by taking A1, right? Compounds for a year, and this is the interesting part, I subtract not 25,000, but 25,000 times 1.05. I've increased the amount that I subtract by 5%, right? That makes this question a little bit different. So then I sub this expression into here, right? And at the same time, if it's okay with you, I'll expand, right? So saves me a step. So 1.03 squared, because there's two of them, minus 25,000 times 1.03 times 1.03, and then minus 25,000, 1.05. All right. Now, all of a sudden, it gets interesting because it's not your typical where it's like 25,000 times 1.05 minus 25,000. It's got two rates in there, right? Makes this question a bit fancier. Now, A3 is where they want me to go, so let's go there, right? A3 equals to, obviously, equals to, so I'll develop the expression starting with A2, bit of compound interest minus, now, this is the second year, the expenses have increased again, so I need to minus 25,000 now, multiplied by 1.05 to the power of 2. Each year, the subtraction, right, increases by a factor of 1.05, right? Let's keep that in mind. Now, what do I do again? I sub this expression now into this guy. And if it's okay with you, I will sub in and expand. So this guy times 1.03, so it's 500,000 times 1.03 cubed, minus now this guy times 1.03, so 25,000 times 1.03 squared. This guy times this guy, so there's one of each bracket, so 25,000, 1.03 3 times 1.05 and minus 25,000, 1.05 squared. Now, is that all they need me to do? Need to be factorized. Okay, cool. They want to factorize 1.5. Okay, cool. So therefore, A3 equals to 500,000, 1.03, and then factorize minus 25,000 out. Now, the pattern here is important. So they want me to do the last one squared first, plus the middle guys. And how did I express it? Because I'm just going to copy and paste. Okay, 1.05 bracket 1.03 plus 1.03 squared. Now, we've got that's part A, right? But normally when we get to A3 in most of the other home loan questions, right, you start developing a pattern for you to then infer, therefore, AN looks like this. I'm not sure about you, but the pattern there is interesting, right? I just need to do, just for my sake, I'm going to do A4 just so I can see what it really looks like. Because right now, it's hard for me to tell where this is going, right? So that's part A. Now, this is not necessary. This is only for me to demonstrate to you. This is how I would teach my students, right? Right now, the pattern, I know it, right? But just in case you can't see it, right? If I develop A4, which is A3 times 1.03 minus another lot of 25,000, but this time 1.05 to the power of 3, right? And if I sub that guy in there, I'm just going to go hasty about this, right? Let's go quickly about this. Whoops. If I sub this expression in there and multiply by 1.03, I'll get 500,000. 1.03 power of 4 minus, now, there are 3 terms here, each one of them multiplied by 1.03. So you get 25,000, right? I'm going to expand it in reverse order. So 1.03 cubed minus 25,000, 1.05, 1.03 squared. You know what? I reverse the order. I just want to show you the pattern. Squared 1.05 minus 25,000. Now this gets a bit longy. 1.03. Multiplying by that, so it'll be 1.05 squared, right? They're the 3 green terms. Just to be clear, they're the 3 green terms here expanded with the 1.03, right? And then minus 25,000. One more, 1.05 cubed. All right, let's see what we have. Now, if I factorize that, you start getting the pattern, right? You go 500,000, 1.034 minus 25,000. Now, this one here, let's do what they did, right? I'm going to put the order 1.05 up here. Yeah, power of 3. So factorize it backwards, right? 0.05 squared, 0.03. Sorry, that's a plus. 1.05, 1.03 squared plus 0.03 cubed. Now, this is nice. Yeah, once you get there, you can see the pattern. It looks like when you expand quadratics and cubics, right? Look at this, right? You can sort of see that within the green, I'll use a green pen to demonstrate, right? Can you see? It sort of looks like a quadratic in that it's like, you know, like when you go x plus y perfect square, you get x squared plus 2xy plus y squared. But in this case, forget about the 2. X squared, xy, y squared, right? That's what it looks like, right? X squared, xy, y squared, yeah? And for those that know, how do you expand perfect cubes? Well, sorry, the binomial cubed, right? That's like x cubed plus 3x squared y plus 3xy squared plus y cubed, right? And if you get rid of the coefficients, x cubed, x squared y, xy squared, y cubed, right? It's like expanding that, right? And another way to see it is you basically take the first number and it decreases by 1 power each time. And then you take the second number and you start from power 3, power 2, power 1 disappears. So you sort of converge, right? Now, that's important because therein lies my pattern, right? So with that in mind, guys, I'm just going to move part B. Not that you need this, right? But I'm just going to move it up here anyway. Up into this space here. Cool. Now, because with that, we're now going to extrapolate or infer, therefore, AN equals 2. Now, there's always two parts, right? Whenever we're doing these questions. Oops. It's always two parts. So I'm just going to move over here. Perfect. The first part is the 500,000. 1.03 to the power of n. Sorry, I'm freestyling. I haven't even read the question, right? Prove that good. How many complete years will Ada be able to withdraw money from this account in order to meet it? So basically, when does it run out of money, right? Yeah. When does AN go to 0? So I need to find an expression for AN first. Now, look at this. In the square bracket, this is where it's at, right? This is where the question's at. So you can see when, and let's develop a pattern by doing this, right? When it was A4, the highest power, the power on the 500 grand is the same. So that guy is the same as N. Perfect. When it was A4, highest power here is 3 on both sides, and then they sort of drop by 1 each time, right? So this is how I'm going to play it out, right? This is how I'm going to play it out. I'm going to go, if that's AN, I'm going to go 1.05 to the power of n minus 1 plus 1.05 to the power of n minus 2, because it's 1 less, and then multiply that by 1.03 to the power of 1 plus 1.05 to the power of n minus 3, 1.03 squared, etc. And then the last one is going to be 1.03 to the power of n minus 1, right? And it's inferred by the steps upstairs, right? Now, at this juncture, you basically say to yourself, I need to develop a GP here, right? That's normally what happens. If you look at that, it's hard to develop a GP here, but so this is a trick. The trick is to factorize, right? From all terms, from each one of these terms, factorize something out, right? I'm going to take out, why don't you try to factorize out 1.05 to the power of n minus 1? Take that out. Let's see where that takes you, right? So, yeah, take that out. Let's see where that takes you. Oh, in my solutions, I actually took out. Now, it literally doesn't matter because it's symmetrical. Let's take this guy out just to make me happy, right? If you take that out, AN equals to 500,000, 1.03 to the power of n, minus 25,000, 1.03 to the power of n minus 1. Now, look what's in here, right? We'll see. Guys, I'll start factorizing backwards if that's okay. So if I factorize this guy from the end, I get 1 plus, right? Now, can I ask a favor? I'm just going to pop in another term just for your visual pleasure, right? So the term before here would be 1.05, because there's one of them, and then 1.03 to the power of n minus 2. Now, because if I factorize 1.03 to the power of n minus 1, that's 1 bigger than this guy, right? And so the term I'll get here is 1.05 divided by 1.03. Now, let me say that again. If you think about it, if I factorize this guy out from this term, which was the second last term there, right? This guy is 1.03 bigger than that. So when I take out 1.03 to the power of n minus 1, I have to divide it, right? There's no term there for me to factorize, so I divide it, and I introduce this 1.03 on the bottom. Now, what that means is every time you factorize 1.03 to the power of that, the next term in, you probably expect it to be that squared, 1.03 squared, like that. Now we're cooking, right? Because you can see now that I have something that resembles a GP, right? I got a common multiple there, right? Common multiple, common ratio, it grows by a factor of 1.05 divided by 1.03 each term, right? And then the last term, if I factorize, 1.03 n minus 1 from the last term there. It'll be 1.05 n minus 1 over 1.03 n minus 1. Because there's no 1.03 terms there, so it'd just be that guy. This is my GP, right? That is a sum of a GP, right? Where the first value is 1. The common ratio is 1.05 over 1.03. And the terms, well, there are n terms, right? Yeah, putting that into my GP formula for the sum of a GP. So let me just scroll down over here. AN equals to 1.03 power of n minus 25,000. There's a 1.03 n minus 1 there. Guys, sum of a GP, it's A times R to power of n minus 1 all over R minus 1. Yeah, that is my expression for n. Now, I know there's one that I need to simplify, but I know I want this question. The question basically asks me, what's the value of n before an runs to 0? So I'm going to set this to 0, and we're going to solve, right? Now, looks a bit messy, but check this out, right? So if I throw this guy over the fence, I get 500,000, 1.03 to the power of n equals to 25,000, 1.03 to the power of n minus 1. Now that one goes away, and it just looks like this sort of messy big bracket of 1.5, 1.03 to the power of n minus 1 all over 1.05, 03 minus 1. Okay. Now at this stage, a few things cancel out. Firstly, that n cancels out with this guy because there's one power less. So I got 1.03 here, and it'd be smart to move this guy over here. I keep missing the 0, guys. It's 500,000. Yeah. Now 500,000 divided by 250, 25,000 is 20. And then I'm also gonna multiply this part here upwards, right? Let's take that upwards as well. So that guy there. Let's bring it up here. Let's see where that takes us. We get, so I'm going to divide this guy by this guy first, and that's 20. I've got a 1.03 there, right? Remaining, and I'm multiplying it by 1.05, 1.03 minus 1, and that equals to 1.05, 1.03 over n minus 1. You can see where I'm going to, right? Basically, move the 1 over, and then log and change the base, right? So I'm going to copy this expression over here so I have more space. All right, let's finish this question off, right? So move the 1 over, and you got 1.05, 1.03 to the power of n equals to 20, 1.03, 1.05, 1.03 minus 1. It's 1. Yeah. And I'm just gonna change the base, right? And log this, right? So n equals to ln. You know what? I was gonna write it, but I can just copy that. Put it into here. Perfect. Divided by ln. Put this into here. Get rid of the n. Yeah, and that's your answer, right? So punch it in the calculator. Let's see where that gets us to, right? And then we'll answer the question. So I believe if you punch that correctly, 17.496. Yeah, check that. That's now, whenever it's a decimal, answer the question. For how many complete years will Ada be able to withdraw money from the account? She can withdraw for 17 years because on the 18th year, she would have run out of money. So therefore, the answer is 17 years. How was that now? I love this question because it got hard, right? It got hard when the series wasn't obvious So if you were stuck on this part here, right? Even if you develop the series here, a lot of people don't know how to go from this blue step down to this green step, right? This blue step, force factorize this guy out. This is the key. Force factorize that guy out, and then whatever's left in the bracket there forms a GP, a geometric progression, right? Once you do that, then it's just messy algebra. Yes, there's a lot of fractions involved, but the aim is to get an equation that we can use logs for. And you knew it was going to be logs because whenever you're doing these power questions and they're finding a number of years and those types of questions, it's going to be log. Guys, hopefully that was a cool question, a nice question. If you like that, please like the video, subscribe to the channel, and tell your friends. I'll see you guys at the next one. Thank you.